You may have come to the unspoken assumption that Ohm's law is a universal law, applicable to all cases where current flows through a conductor. You may think that the ratio of voltage and current in a circuit remains constant at all times for all combinations of V and I. But this is not really true. In this video, we will look at how applicable Ohm's law is to various scenarios we encounter in electrical circuits. At constant temperature, the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance of the conductor. In other words, I is equal to V upon R or R is equal to V upon I. This gives us a relation between current, voltage and resistance. We can apply Ohm's law or the Ohm's law triangle to such materials, allowing us to find the voltage or current or resistance as long as any two of these are already known to us. Examples of such materials are the copper or aluminum wiring that we use in our homes and offices. If you look at the voltage current graph for such a material, you will observe that the slope of the graph remains constant at all points. That means that the increase of current in response to an increase in voltage is always proportional, and this proportion does not change for any point on the voltage-current relationship. Let us look at a device which actually follows this rule. This is a laboratory resistance box, which contains a metal wire that is selected to be extremely stable with resistance. So Ohm's law is valid only if the resistance of the material remains unchanged in response to the voltage or current passing through it. Let's look at some cases where this assumption of constant resistance does not hold true. For example, here we have the graph of a normal ohmic conductor whose temperature is not being kept constant. For example, if you were to pass a current through the tungsten filament of a bulb, it would get very hot. At this high temperature, the resistance of the metal will increase greatly, meaning that the voltage needed to drive a current begins to increase non-linearly, as you can see here. So we see that even for an ohmic material which obeys Ohm's law, will fail that law if the temperature changes due to the current passing through the circuit. Another possibility is that the resistance of the device or the material changes not only non-linearly, but also in addition depends on the direction of the applied voltage. Take for example the graph of this semiconductor diode. In this device, we see that the behavior of current in the forward and reverse regions, that is, in the direction of positive voltage and negative voltage, are very, very different. When we are applying voltage in this direction, which we call the positive direction, the current does not increase linearly. This is clearly not a straight line. Second, the current increases only after a particular voltage is reached. This is called the threshold voltage and increases very quickly once we reach the threshold voltage. On the other hand, if you were to reverse the direction of voltage, you were to apply the connections in the opposite direction, we observe that not only is the current much lower than the forward direction, we also see that the current stops increasing after a particular point. So clearly, in this device, resistance is not only variable, but it is also depending on the direction of the voltage and current flow. The third case where Ohm's law fails us is with devices whose voltage and current relationships are not strictly increasing nor decreasing. For example, in a semiconductor like gallium arsenide, which is used for all kinds of things like LEDs and camera sensors, the resistance can be positive in some regions and negative in other regions. As you can see in this graph, as we keep increasing the voltage, the current first increases almost linearly, like an ohmic device. But then we observe that the current starts stabilizing at a particular value and then starts decreasing. So we see that the resistance is first low and then high with an increase in voltage. So this is extremely vital for us to ensure that we understand the electrical circuit in detail before we apply Ohm's law to it. There are some materials and devices which will hold the proportionality for V and I, and some which will not.
Manorama Horizon. Learning made simple.